Hi everyone, my name is Ayush Pandhi. I'm a grad student working out of the University of Toronto, and I'm going to be talking to you about a method for reconstructing the galactic magnetic field using observations of fast radio bursts and active galactic nuclei. Okay, so just quickly some background. When we have a polarized source of light, we can measure the change in polarization angle between two observing frequencies, as well as the time delay, which will give us the rotation measure and dispersion measure. And using these two quantities is one of the ways that we can derive the electron density weighted parallel magnetic field. And we've been using this as a probe for the galactic magnetic field, mainly with pulsars. But if you only have RM measurements, that can tell you whether or not the magnetic field is pointing towards or away from you. But if you also have the dispersion measure along that same line of sight, then you can get a full estimate of both the direction and strength of the parallel magnetic field. So again, like I said, we've mostly been studying the galactic magnetic field with this probe using pulsars, which are already in the Milky Way. So they have a few downsides. The first being we don't really have too many of them that you can see here. And also the fact that they're within our own galaxy means that they don't probe the entire galactic magnetic field. They only probe the distance out to the pulsar itself. We have some probes of extragalactic RM, which you can see 50,000 or so AGN, but we cannot get dispersion measure from AGN. So until recently, we didn't really have a good probe for extragalactic dispersion measure, but now we're starting to get a lot of fast radio bursts. So specifically the CHIME FRB collaboration released a catalog just this year of about 536 FRBs, and this number is expected to increase very fast, not just with CHIME FRB, but also with future radio surveys like the SKA. So what we're going to try to do in this project is to simulate populations of AGN and FRB and come up with a method to infer all-sky parallel magnetic field observations. So this would be similar to something like the existing all-sky Faraday rotation maps. But now we're using joint inference algorithm between both the DM and RM. So the first step in that is simulating populations of AGN and FRB. So for the AGN, it's quite simple. We already have a population of AGN we can pull from, so we'll just take the 50,000 or so AGN data points that we have. We'll take their positions and we'll take their rotation measure errors, which you can see plotted here in RA and deck coordinates. And then we'll generate simulations along the line of sight to each one of those points. For the FRB population, there's a nice little package that we use called FRB Poppy. And what that lets us do is create FRB data sets that with a variable size. So we create a data set of the smallest being 1,000 FRBs, which should represent the very near future of how many FRB observations we would have. And then to the largest data set of about 50,000 FRBs, which would match how many AGN observations we roughly have at the moment. And what we can also do with this package is apply a filter that would simulate a subpopulation of FRBs that would be observable by a certain radio survey. So in this case, since CHIME is the current radio survey observing the most FRBs, what we do is we apply conditions for CHIME observations, but apply to the entire sky. So that looks something like this. And in this plot, again, in RA and deck coordinates, we've simulated about 100,000 FRBs, so the gray points in the background, and around 1,300 of those would be observable by CHIME, if CHIME could see the entire sky. So that's what's shown in blue. Okay, now that we have our AGN and FRB populations, we have to simulate the RM and DM observations to their lines of sight. So to do that, we start off with galactic magnetic field and thermal electron density models. So from literature, we use the Janssen-Farr 2012 model for a galactic magnetic field. And for thermal electron density, we use the Yao et al. 2017, as well as Yamasaki and Totani 2020 models for the disk and halo DM components. And if we plug those into the Hammurabi X package, we will get our assumed DM and RM skies. Then we also have to account for extragalactic contributions, particularly to the DM, which will have a much larger extragalactic contribution than the RM. So for contributions from the IGM, we use the DM redshift relation presented in McCart et al. 2020, which is shown on the right here. And then for the host contribution from the host galaxy of the FRB, we sample from a normal distribution that scales as 1/1 plus the redshift. So you can see this plot on the right shows in black the IGM contributions to the DM, and in gray the host galaxy contributions to the DM as a function of redshift in our simulated population. And for the extragalactic RM contributions, we follow Opperman et al. 2015, and using their results, we sample from a normal distribution between -7 and +7 radians per meter squared. And for any given line of sight, we just sample from that distribution and use that as our extragalactic RM. Okay, so now that we have all of our simulated observations, now we have to build up our joint inference algorithm. So I won't get into a ton of the details with this. It gets a little bit complicated, but essentially the situation that we're in is that we don't really have knowledge of the DM or RM sky except for the largest scales or along specific lines of sight where we have the observations. So what we do is we infer both the RM and DM sky non-parametrically using simple models for the galactic RM and DM, which are shown at the bottom of the slide, and generic assumptions for priors. And then at the end, what we'll do is parameterize each of the DM and RM sky maps as a nonlinear combination of Gaussian sky maps. And then using those, we can estimate what B parallel sky map would look like. Okay, so these are some of the results that we have. In the first row is just directly from our model. So that's the baseline model that we're trying to recreate using our simulated observations. So that's the DM sky on the left and the B parallel sky on the right. And in the middle row is what we get if we use a reconstruction algorithm with 50,000 FRB and 50,000 AGN. And then the bottom row is the same number of AGN, but with only 1,000 FRBs. So we're testing with variable numbers of FRB dataset sizes. And as you can see, it gets the large scale galactic DM right, but the largest problem we run into is that we get a ton of extragalactic DM contributions along basically all lines of sight. And what that will do is it will underestimate the B parallel in our all sky galactic magnetic field map. So one of the ways we counteract that is we take equal area bins along the sky, and what we do is instead of using all of our data points, we take just the lowest DM data point in each one of these bins and use that as a representation of what the sky would look like in that bin. And what that essentially does is it helps us minimize our extragalactic contributions to the DM. So if I flip between these slides, you can see particularly in the middle panel, our extragalactic DM goes down by quite a bit. And this helps us recover some of the galactic B parallel structure as well. And obviously this technique works a lot better given more data points. So with only 1,000 FRBs, you're only really reducing that number down to like 600 or 700 FRBs using this technique. So it doesn't get rid of a ton of extragalactic DM contributions. So what that looks like as a function of latitude is plotted here. So again, here the gray points are representing our model. So that's what we're trying to recreate. The blue points are from a reconstructed all sky DM map. And then the red points are what happens after we apply this minimization of the DM by taking equal area bins on the sky and taking the lowest DM from those. So effectively, those light red points are giving us an upper limit on the total galactic DM. There have been other studies that have looked at the ISM contributions to the DM, specifically the most recent being Opera et al. 2020, which model the DM ISM contribution as this here, so about 23.5 over sine B. So if we take that number, and again, this would be a lower limit to the total galactic DM because it's only looking at the ISM with pulsars that are embedded within the galaxy. So if we take our DM observations and we estimate them as this model here, and then apply a correction based on that, we get these hollow red points. So this correction would give us a lower limit on the total galactic DM. If we generalize that one step further, instead of having 23.5, which is derived from pulsar observations, we just leave that as a free parameter and fit our DM observations along a given line of sight as this equation here. Then what we can do is apply a correction, which shows these bright red points here, that gets as close as possible to reconstructing the underlying fields as we can. And again, in this model, our 1 over sine B dependence for the galactic DM breaks apart as we get close to the galactic plane, so B getting close to 0. So we only apply this correction for galactic latitudes greater than 10 degrees. And this plot shows what those DM corrections would look like in terms of helping us recover the B parallel values at different slices of galactic longitude. So you can go through this plot. The colors represent the same corrections with the hollow, the light, and the bright red points. And as you can see in all of these, the corrections do help us recover almost all of the galactic B parallel structure. Okay, so that's everything from me. This was a bit of a short summary. So if you do have questions or any further discussion you want to have, I've put my email at the start of this video, so you can just go back there and feel free to contact me about that. But yeah, thank you for listening, and I hope you enjoy the rest of the conference.